Yeah, welcome to this session of this workshop, this conference. So now we have Professor Joe Bhaseen from King's College London talking about stochastic approach to quantum spin dynamics.
Thanks very much. It's a great pleasure to be here, and thanks very much for the organizers for organizing such a wonderful conference. This is my second time in Bangalore, and actually the first time was incredibly stimulating and raised some questions which I will touch upon but not fully address in this talk. Is there an echo? Is that actually okay? Is that okay? Fine, okay. So this is work I've done over the last few years with a couple of my graduate students, Stefano De Nicola, and more recently Sam Begg, and most of the work that I'll talk about in this lecture is Sam's, and also with Ben Doyen and Andrew Green. So, as I said, I was here a few years back before the pandemic kind of interrupted all of our travels, and I'd like to also kind of acknowledge very helpful conversations with Duncan. I think in the seminar, he asked me whether the things I was talking about were connected to a so-called positive P approach, okay? So it's a technique that one of his colleagues, Eric Sorensen, had worked on, and it turns out that there is a connection, okay? I'll just verbalize what the connection is rather than taking you through all of the links to it, okay? But the essence of what we're going to look at is trying to look at the dynamics of quantum spin systems via classical stochastic processes. And if you look in the literature, there's obviously a lot of work of people using phase space techniques, classical techniques to try and simulate quantum spin systems. And very often what you do is you think in terms of a probability distribution or some effective probability distribution on that phase space. And so it's very natural to start from a Fokker-Planck equation. In this approach, we're taking a Langevin approach, okay, and you can also derive a Fokker-Planck equation, but in many respects, it turns out to be equivalent to solving the Schrödinger equation, which is actually rather challenging, okay? So there's a formal link between these different approaches. I'll flag some papers where we discuss this, but I'm not going to spend a lot of time discussing that connection, but depending whether your background's in quantum optics or classical phase space techniques, you might find those connections interesting. So here's the series of papers, okay? So I talked a while ago about this kind of precursors to this work, where we tried to set up this problem and see if we could numerically solve these stochastic differential equations and see whether we could track exact non-equilibrium quantum spin dynamics. And then we've developed this in a series of papers. This emphasizes that actually this is kind of a strange representation in that it's formally non-Hermitian in spite of the fact that you're trying to follow unitary dynamics, okay? It only effectively becomes unitary dynamics if you average over a large number of stochastic samples, and at some stage, the non-hermiticity comes to bite you because you will see that the simulations eventually break down at sufficiently long times. Okay. I should also say, like all approaches to quantum many-body systems, there's very rarely a free lunch, and there definitely isn't here. It's good at doing certain things. It's not so good at doing other things, and I'll try and unpack that as I go along. What interests me about this approach is that it's applicable to systems in arbitrary dimensions, and also it doesn't really care whether the system is integrable or non-integrable. So if you think about a lot of the insights we've got over the years into the dynamics of quantum systems, very often we start looking at some solvable point in order to get some traction on it. Here, I'm kind of interested in the technique because you can actually write down these exact stochastic differential equations for an arbitrary, almost arbitrary quantum spin system, at least if it's got quadratic spin interactions, and write down formally what the evolution equations are. And I don't know too many instances where you can do that for a problem that's not exactly solvable. So these later papers, again, I'll also allude to what it is that we do. Roughly speaking, when we're solving these stochastic differential equations, you can imagine asking about whether there's a suitable reference trajectory to expand about. So if you think about when you solve things using path integrals, you very often, maybe if you're doing semi-classics, you expand around a classical path. It says there's a preferred trajectory which you expand around. There's something very similar in the stochastic approach. And it turns out that it's related to thinking about a Weiss field for your spin. So when you think about solving problems of ferromagnetism, you think about the effective field that acts on your spin due to its neighbors, it turns out there's a parameter you can introduce into these stochastic differential equations, which enables you to go a little bit further. And this most recent work is an extension of this, pointing out that you can actually choose this vice field on a trajectory by trajectory basis. Okay? And if you think about in the path integral language what that means, I'm not aware of any problem where you would choose a reference trajectory in a path integral that's different for every single path that you sum over. Okay, so if anybody has seen something very similar to that in path integrals, I'd be very interested to know. The point is that with this extra parameter, we can push the simulation times somewhat further. Okay, and it turns out there's an analog in these space-based approaches, which are often referred to as drift gauges. It says there's some redundancy in your parameterization that you can exploit and get better results. Okay, so the outline of what I'll talk about is I'll give you a kind of introduction to this approach. Okay, I think most of you probably won't be so familiar with this. Certainly when I learned about this, I wasn't familiar with this technique. It wasn't really on my radar. And I'll try and explain to you why this is useful both in and out of equilibrium. And I first learned about a kind of baby version of this approach from John Chalker. Okay, he was working on, so John is obviously an expert in frustrated magnetism. He was interested in trying to think about how to describe single clusters of quantum spins. And he developed an approach to this based on stochastic differential equations. And it turns out that this generalizes to more complicated problems, and that's what we're going to look at. And the example I'm going to focus on is dynamical quantum phase transitions, not just because of the topic of this workshop, but also because it's the simplest thing that you can look at within this approach. Okay, it's basically, we focus on the so-called Loschmidt amplitude, the amplitude to return to a given state. It places the evolution operator at the heart of the proceedings, and that turns out to be something that we can describe using these techniques. Okay, and what I'll do is I'll then conclude eventually with some current status and future developments. Okay. And if there's any questions, please don't hesitate to interrupt. So as everybody knows in this audience, right, I mean, there's kind of a lot of reasons for looking at quantum spin systems. Very often you look at them because they're just simple tractable models to get a little bit of intuition into, for example, notions of thermalization, but perhaps also more recently with kind of rapid advances in quantum information and quantum computing, these kind of techniques are potentially relevant for benchmarking 2D, 3D systems, as I'll show you, quantum devices. I should also say, I didn't prepare a slide on this. We have a postdoc in King's with myself and George Booth to start actually probably in the next few months, probably 1st of October, to look at trying to develop quantum software for implementing fermionic systems on quantum computers. So if anybody in the audience is looking for a postdoc or you've got good postdocs in mind, just send them our way. The deadline will be rather short, early July, so please tell them to get in touch immediately. Okay. So let me take you through this kind of toy example. Okay, it looks a little bit trivial, but as I'll show you, all of the relevant physics is contained in this simple toy example. Okay? So as I said, John was working with the student Patrick Hogan on trying to understand the thermodynamics of a single cluster of spins. Okay, the logic being these little clusters, let's say you're interested in a pyrochlore lattice, they're built from some tetrahedra. So they're, if you look at the interactions between a spin on these vertices, typically you'll have all of the spins interacting with all of the other spins in that given tetrahedron. Okay. So if you ask what does that look like then as a Hamiltonian, you can write this in this very compact form. It says, add up all of the spins in that cluster and square it, and you'll generate all of the nearest neighbor interactions, and the diagonal terms will just be constants, SI squared. Okay? So it says your Hamiltonian then can be expressed in this form, that it's one big spin, S total, just some of the spins in that little cluster, all squared. And John was interested in computing the thermodynamics of this little cluster. I mean, obviously, it's only a tiny little unit, so you're not really interested in kind of thermodynamic limits of this, but you can formally construct the partition function. There's a bunch of eigenvalues, degeneracies, and you can imagine trying to compute the partition function. And what you'd probably do if somebody gave this to you as a problem is you'd probably do it by just addition of angular momentum, okay? But John did something rather neat, okay? He said, well, let us regard this as an interaction and let's decouple it using a Hubbard-Stratonovich transformation, okay? So it's just essentially a Gaussian integral. You've got some term h squared, and you've got a term h dot s, and you do the integral over this Hubbard-Stratonovich field h, and you'll generate s dot s, essentially, okay? So this is, we're interested in thermodynamics, so we think of this in a path integral formulation where we integrate over imaginary time on the interval 0 to beta, and then we integrate over all of these Hubbard-Stratonovich fields. So what it says is that we've traded the interactions in this little cluster for this auxiliary field h, and then we integrate over that and we recover our original problem. Now you look at that and your immediate reaction is, why do this, okay? And the answer is that if you look closely at this problem, what you've effectively done is decompose this into a single spin interacting with a magnetic field that is Gaussian distributed. Okay? So it says you can trade interactions for fluctuating fields. And so if you can now solve the appropriate problem for this spin coupled to a magnetic field and fluctuating, you can actually construct the exact partition function of this little cluster. Okay, and that's the basic idea, and that idea pervades into arbitrary dimensions, integrable, non-integrable problems, as long as it ends up as something quadratic that you can decouple in this way. Yeah. Very good. So John was interested in this. So in the case of a tetrahedron, Q is 4, okay? And actually, in general, it doesn't actually matter. Very often when you're looking at, say, problems in frustrated magnetism, you want a certain kind of, you're interested in how ground state properties vary as a function of the number of degrees of freedom. You very often do Boltzmann counting arguments. So it's helpful in some cases to have Q as a free parameter. For us, it will just be set by whatever the geometry of the lattice is. Okay. Yeah, thanks. Okay, so here, what you see is that what's central then to this Hubbard-Stratonovich transformation is this exponential of h dot s. And if I was a little bit more careful with the path integrals, there's a time ordering operation in there. So this is the usual evolution operator. Okay, and at least for this part of the talk, I'm just using the notations that John used. This capital T is just the evolution operator, and I'll call it U a little bit later. So if you think about, most of the problems you're interested in, whether it's flow K, whether it's some driven system, whether it's some quench, okay, you're typically interested in this evolution operator, how it acts on your state and how it then gives rise to non-trivial, non-equilibrium dynamics. And so what it says is that this is basically telling you that you can extract this partition function by taking a stochastic average of this evolution operator. Okay, that's what it's saying. So let me just kind of formalize this a little bit more. Okay, so it says that this partition function is this integral over these Hubbard-Stratonovich fields, they're Gaussian distributed. You take the trace of this evolution operator, and if you've got Q independent neighbors, then this is just replicated Q times. Okay, so we're going to introduce this notation. These angular brackets mean do this Gaussian average, and so your partition function then says evaluate the trace of this evolution operator, raise it to the power Q, average over these Gaussian fields. And if you look at John's paper, what he did is he did something very clever, okay? And I didn't realize how clever it was that in the context of this simple example, but it turns out to actually be very clever. So what he says is this time-ordered exponential is normally a headache, okay? Spin operators Sx, Sy, Sz, they don't commute with each other. And the way you keep track of this is through this time-ordering operation. And John noticed that this time-ordered exponential is basically a group element. And so you can therefore parameterize it in terms of your favorite parameterization of SU2. Here he's choosing Euler angles. So you end up with some parameters alpha, beta, gamma that are in effect related to your original Hubbard-Stratonovich fields, but it's a little bit more simple because you don't have to keep this time-ordered evolution, this time-ordering operation. Okay? Somehow it's implicitly embedded into this representation. And so what he derived is a set of stochastic differential equations for these coordinates, alpha, beta, gamma, okay? So you see these are time derivatives. There's some function of these angles. This is your choice of parameters, okay? Here he still has these Hubbard-Stratonovich variables appearing in this particular representation. And you see you have both multiplicative and additive noise, okay? So if you compare this to, kind of standard Langevin type equation, it says you've got some time rate of change of some coordinates. In the Langevin equation, it'd be some velocities, and you have some noise terms which are buffeting your coordinates around. So if you can solve this set of SDEs, then you can formally construct the partition function. And so what John did was to switch gears at that stage and say, let's not do that, okay? Let's rather think about the probability to land at a particular position in this SU2 manifold. So he calls it capital Q. You've got some coordinates alpha, beta, gamma. There's a certain probability to land at a given place. And you can write the same thing down by now averaging over probability to land at a particular place times this evolution operator evaluated at those coordinates, okay? And for John, for that simple problem, that was much easier to solve than the SDEs. For us, when we're going to look at lattice models, it's actually easier to numerically solve the stochastic differential equations rather than solving the Fokker-Planck equation. And so in this toy example, the Fokker-Planck equation essentially looks like a kind of diffusion problem for motion on this manifold. This delta squared is just the Laplacian on SU2. You've got some particular parameterization, so you look at del squared, and quite a lot is known about eigenfunctions and eigenvalues of Laplacians on different group manifolds. And so if you run with that, you can write down a formal expression for this partition function in terms of these variables little j. They're essentially counting, you know, the kind of different spin states you can get from addition of angular momentum. And you've got some weight, which is not that pretty, okay? It still involves some integral representation over some coordinate psi. But the point is you can formally reconstruct the exact partition function, okay? So why is this important? It's important because it shows that you can formally encode exact, in this case, quantum thermodynamics via this stochastic process. And what I'll show you is that you can also do this for dynamics, and essentially it works exactly up until you're unable to sample the problem efficiently. Yeah. So this is not time, so very good, okay? So in the problem John was considering, he was actually interested in thermodynamics. So this was already in Euclidean time. Okay, so one thing we want to do, okay, my former student Stefano actually has a paper on this. A very natural thing to do is to see whether you can use this approach to look at ground state properties. Okay, so then you have to evolve in imaginary time. The difficulty is it actually turns out to be non-trivial to get to sufficiently long imaginary times to actually converge to ground state problems. But in principle, this formalism ought to apply. And one of the things we've been looking at is whether or not we can actually do that. So good. So the original example was not for dynamics, it was for thermodynamics. Yeah. Okay. Okay, so now let's switch gears and do dynamics, okay? So sometime after that paper by John Chalker, there was a very nice paper by Vladimir Gritsev. There was also a paper by Victor Galitsky. I think Victor had actually been chatting to Vladimir at some point. So there's an approach to trying to think about this technique for arbitrary quantum spin systems. And so here you just have some generic Heisenberg type model, okay? I should say that for what I'm studying, most of what we'll focus on is Ising models, okay? Transverse field Ising models. In principle, all of these things can be done for Heisenberg systems, but you end up having to decouple more interactions, okay? So it's not just that because we've done it for Ising, you can immediately go and run and do this for XXE. Formally you can, but there's a little bit more gymnastics you have to do because you've got more decouplings, okay? And these spin operators obviously obey non-trivial commutation relations. And again, what you're interested in is this time-ordered exponential. And in general, this is non-trivial to deal with because of this time ordering operation. But if you follow the logic that we've just gone through, okay, it's kind of clear what you should do. It says, well, let's take that evolution operator, let's decouple the interactions in H via introducing these auxiliary fields that we're going to call phi, okay? So I'm switching gears because usually you use the symbol H for external magnetic fields. So let's call the decoupling variable phi. And what you see is that this is now linear in these spin variables. That's what you wanted, okay? Because in order to perform the trace, okay, when you want to work out, for example, partition functions or correlation functions, it's advantageous to have these spin operators decoupled. But the price you pay for that is this Gaussian factor that we'll refer to as the noise action, okay? But this is formally exact, okay? There's no approximations in there at all. It's just a formal decoupling of the spins and saying that this spin interacts with the stochastic magnetic field, and the interactions determine the kind of variance of this distribution. okay? The other thing I should say as well is that I've got to be a little bit careful, because you see there's all these eyes floating around. We're looking at a time evolution problem. So generically, all of these fields are complex. So it's not just some standard diffusion problem that you would meet in a kind of classical context. It's a little bit more subtle than that. But nonetheless, formally, it's just some classical process involving these variables phi, these decoupling variables. Okay. No good, and actually constraints will be an issue, okay? So one thing that we can see is that if you go to late enough times, the norm is preserved up until a critical time when it's not, okay? So what it's saying is that imposing those constraints is non-trivial, okay? But it's also an interesting question, and we have asked this, okay? You could imagine trying to impose all sorts of symmetries and constraints on the evolution, okay, to see whether or not you actually enable yourself to get to longer times in the dynamics, okay? The difficulty is if you imagine introducing a constraint, you introduce a Lagrange multiplier, it's yet another variable in your formalism that you need to keep track of. But in principle, you can think about imposing constraints. I think one reason we didn't is there is some analog of this in the literature where people imposed constraints and actually it didn't help you. You ended up with trajectories that were diverging as a result of introducing your constraints, okay? But in principle, it's a good question. Ghost issues. Yeah, no, there could be. I'll show you a little bit about how this breaks down, what is kind of responsible for it, okay? But as I said, what I'm interested in is, you know, if you can run this procedure on a 2D quantum spin system or 3D, okay, it's already kind of interesting because the formalism just doesn't care. Okay? The breakdown time does, and how difficult it is to evaluate the stochastic averages, but the actual formalism doesn't care. Okay? So here, again, we've got this similar problem. It's this average of this time-ordered exponential. And now you see that this capital phi is a function of your decoupling fields, the noises, plus any fields that you apply. Okay, so it's still of the form e to the minus h dot s, okay? But that h has a combination of externally applied fields and the effective magnetic fields that you generated by decoupling the interactions. And again, we're now going to use this trick that this time-ordered exponential can be recast as a group element, okay? So here we have some coordinates, psi plus, psi minus, psi z, and it's a particular parameterization. And so Vladimir Gritsev referred to this as a disentangling transformation. But what you see is it's basically what John was doing, which was very natural in the context of a single cluster. It just says, let's not work with this time-ordered exponential. Let's just regard this as an element of SU2 and introduce some new coordinates psi that we'll keep track of. And these are going to be the variables that appear in our SDEs, okay? So if you now run with this, okay, these are the stochastic differential equations that appear in Vladimir's paper. And what you see is, you know, they're very clear. They're non-trivial, but they're clear. You have some rate of change of these coordinates, like we had in the Langevin equations. You've got these noise terms appearing both additively and multiplicatively. But you've got this set of coordinates who you want to iterate forward, and subject to some boundary conditions that depend on your initial spin state, okay? So here, if you look at these equations, these are just standard kind of SDEs, okay? You have some drift term and some noise terms for these coordinates. And the question is, can you solve this set of SDEs numerically? If you could solve them analytically, even better, okay? But, you know, chances at least at the outset are not so great, okay? Can you solve these SDEs numerically and show that you get exact quantum dynamics, okay? And so that's what we did, okay? So again, just to kind of reiterate, it's an exact formulation of quantum dynamics. We've not made any approximations, okay? You're not necessarily going to be able to run it to arbitrary long times because the difficulty is going to be how many samples do you need in order to get to the timescales you're interested in. But essentially, we decouple the interactions using Arbiter-Trzonovich transformation. We disentangle the evolution operator using group theory, and then expectation values or physical observables are expressed in these coordinates. You solve the SDEs, take the classical average, that gives you quantum observables, okay?
Just a quick question. Can you go back to the system of equations? So where in here is the information about the interactions between the spins, the original interactions?
So good. So yeah, but excellent. So these original noise variables are actually correlated noise variables, because when you disentangle them, the interaction matrix appears in the kind of denominator of that quadratic form. In practice, what you do, and I didn't state this, so thanks, is you then diagonalize that noise action. So your SDEs end up with Gaussian noise, so you can sample them efficiently, but then you transfer the problem into these coefficients A and B. So thanks.
Okay, thanks.
Yeah. So the original stochasticity is actually the interactions in your non-stochastic model. Okay, so take a Heisenberg model. The interactions between two spins involve an exchange interaction. So it's J times SI dot SJ. You decouple that interaction using a Hubbard-Stratonovich field, and those Hubbard-Stratonovich fields are Gaussian distributed by hand, because that was your Gaussian integral. So what you do is you take your original unitary dynamics, non-stochastic problem, but by invoking a Hubbard-Stratonovich transformation, you end up with a bunch of spins interacting with these Hubbard-Stratonovich fields that are Gaussian distributed. That's your source of stochasticity. Okay, so it says that the original interactions, you can think of this in a kind of dual formulation. And in fact, actually, by the way, it also means that this technique could also be interesting for introducing other sources of stochasticity. It could be noise, okay, it could be disorder. In principle, all of these things will couple into your SDEs in a very natural way. Okay, is that okay? Okay. So then can we solve these SDEs? Okay. So let me give you an example of an observable that it's very natural to look at in the context of these. Yeah, sure. Yeah, you can formulate them in both the Ito formalism and the Stratonovich formulation. They're in Ito, yeah. Okay. So thanks. Yeah, I mean, actually for numerical purposes, I mean, obviously some formulations are actually better than others. I should also mention as well, I mean, one of the things that we managed to do to actually improve on our early numerics, Sam implemented higher order integration processes for these stochastic differential equations. Also, there's a formal problem in the SDEs that as written, depending where you are, the coordinates, they're parameterized where your spins are on the block sphere. So it turns out that for some parameterizations, when your spin goes to the North Pole, the coordinates actually diverge. This is very bad because then your simulations break down. So in the later works, we introduced a two-patch parameterization of the block sphere so that if you switch across the equator, you have a different parameterization. That just helps eliminate formal divergences in the SDEs so that you can push them again for longer times. Yeah. So we're going to look at this Loschmidt amplitude, okay, and this cropped up in some previous talks, okay. So the idea is you have some initial state, you time evolve it, you look at the overlap with your initial state, and the point is the evolution operator is center stage. And we have a technique that's really good at disentangling things with evolution operators. It gets more complicated for correlation functions because you're going to have more of these evolution operators floating around for forwards and backwards evolution in, say, a Heisenberg type picture. So what you normally do is you say, well, the kind of, unless you're kind of localized or MBL, many body localized, you're going to have some exponential suppression of your probability to return to your initial state. So you very often use this large deviation form. You introduce this so-called Loschmidt rate function. Okay, so you say this amplitude is exponentially suppressed in the system size, and let's look at this quantity lambda of t. Put differently, lambda of t involves the log of this quantity. And what you see immediately is this looks a little bit like a partition function, okay? You look at the free energies minus kt log z. This is very similar with this amplitude playing the role of your partition function. And so many of you will be aware that actually on the back of this analogy, Marcus Heil and Stefan Korine and Anatoly Polkovnikov then introduced this notion of a dynamical transition where in much the same way as you can have a thermodynamic transition as a function of temperature, now you can have dynamical signatures in this Loschmidt rate function as a function of time. Okay, and that's what we're going to see if we can reproduce. Okay, And just to kind of highlight, I know there's a lot of students in the audience, there's some kind of nice papers by Marcus and Anatoly and Stefan, where they go through this in a very pedagogical way. But the idea is that this rate function, as it's called, this lambda of t, shows non-analyticities at certain characteristic times, okay? And so in much the same way that you think about quantum phase transitions usually in equilibrium as a function of a control parameter, here you're thinking about the possibility of transitions occurring dynamically as a function of time, okay? And typically you see these non-analyticities if you quench across an equilibrium phase transition, okay? So this is also just to show that, you know, there are experiments seeing this. This is some experiments from 2017 by the Innsbruck group, where they have a kind of calcium ions in a trap, and they can change the range of the interaction by coupling to some kind of motional degrees of freedom. But essentially, they're looking at a transverse field Ising model where they can quench from a ferromagnetic to a paramagnetic phase, and you see these non-analyticities emerging, okay? So let's now try and set this up for these stochastic differential equations, okay? So if you want to do this, okay, it's very natural to start with the Ising model. Consider, just for simplicity, ferromagnetic interactions. You have some transverse field, and for most of what we'll consider, we'll just consider starting in some simple ferromagnetic state, okay? In principle, you can start from arbitrary states, and we discussed this in our papers, but then, for example, if it involves some superposition, you've got to then kind of iterate the equations with the appropriate boundary conditions in order to start from some generic initial conditions, okay? And so if you look at then this expression for this Loschmidt amplitude, it has a very simple expression in terms of these coordinates. It actually only formally depends on this coordinate psi z, and you want to average that over the stochastic process, okay? So if you can do that, it's saying you can extract this Loschmidt rate function, okay? And so this is what we do. Here's just showing a toy example, okay? We'll go to much bigger system sizes in a minute. This is just showing an example for 7 spins. You take 10 to the 5 realizations of the stochastic process, and you can see very nice peaks in this Loschmidt rate function, okay? If you go to bigger system sizes, you can also do this, and we have much bigger system sizes now, okay? But again, you see that if you choose your number of samples appropriately, you choose your time step appropriately, you can see these non-analyticities, okay? And there is a kind of important point, which is if you undersample your SDEs, okay, in this particular example, you don't fully resolve the peak. It's a bit hard maybe to see at the back, but the ED doesn't quite match your SDE results, but it comes back to the exact answer later on. So what it's saying is this approach is exact, but if you want to resolve a very fine feature, this non-analyticity, you'd better sample enough in order to resolve that, okay? So this is a comparison showing 10 to the 5 versus 10 to the 6 stochastic realizations, and you see that it's not a problem with the method, it's a problem associated with sampling, okay? So here now I'm showing you some kind of more recent results where we push this to some bigger system sizes. Here showing something for kind of 50 sites and 75 sites. And I should emphasize that actually, you know, obviously for something like that, if you wanted to work in 1D, you just use DMRG. For the smaller system sizes I did before, you just use exact diagonalization. It's not that this method is quicker than any of those methods or better, okay? And actually for some problems, it's going to be even worse, okay? What I think is interesting is, as I said, this approach doesn't care about the dimensionality. And so if you imagine trying to extend tensor network methods into higher D, you've got to be able to contract indices in those higher dimensions. It becomes rapidly non-trivial. Here, it's just a direct implementation of the same set of stochastic differential equations, okay? And what you can see in this inset is a comparison, the dots are stochastic differential equations. The comparison is to this matrix product operator technique, and this is the n tends to infinity limit. You see that the matrix product matches exactly the SDE, and both fail to resolve the non-analyticity in the thermodynamic limit because they're both dealing with a 75 site system. So this is not a failure of the stochastic approach. It's just a statement that if you do this simulation for a 75 site system, you don't properly resolve those results to get results in the thermodynamic limit, okay? Yep, okay. So this is showing similar results in 2 dimensions. Obviously, it gets harder to compare to other methods, okay, because you rapidly run out of things you can compare to, but nonetheless, you see the same features, okay? And what we've been able to do more recently in these later papers is extend the simulation times quite substantially by using these Weiss fields, okay? What it says is you can introduce an extra parameter into these SDEs whose job is essentially to track the mean field dynamics. This is like a suitable reference trajectory to get better results, okay? And it's not to say that your dynamics is mean field, it just says that you've got a choice of reference trajectory and you're entitled to choose it however you please. And if you come up with a good prescription for choosing this, well, that's great, okay? So this then is just an advert for those results. And here's some unpublished results showing this for a 3-dimensional system of 125 spins, okay? So you see very clearly, this method doesn't really care about integrability. Okay, you can apply it in the same way in different system sizes, but actually getting to late times can be challenging. Here you can see that there are some fluctuations because it's a stochastic process, and you'd have to go to even more stochastic realizations to try and improve upon these results. But what you can see is that choosing this parameter, the so-called Weiss field, on a trajectory by trajectory basis gets you much longer timescales than choosing this for the ensemble as a whole. Okay, so it's a very different kind of mean field theory that I've not really encountered anywhere else, and it could be that that actually has some applications in other areas. Okay. So this is just to illustrate some results that you can do other observables. As I said, if you want to look at something like the magnetization, you have to introduce both forwards and backwards evolution operators. Now you have to decouple both of those. So you end up with 2 sets of variables that we call phi and phi twiddle. Like before, we had these disentangling variables that made our evolution operator look nice. So now you've got to average functions of these classical variables over these 2 sets of noises, phi and phi twiddle, but it can be done, okay? And although I'm not going to dwell on this now, it turns out that although this formula looks a little bit ugly, actually the formulae are relatively simple, okay? It turns out that you can think of these coordinates in terms of projections of the block sphere and write down observables in a very natural way. And then the question is, can you then average that observable over the stochastic process to get what you're interested in, okay? And so it's much harder to do things like magnetization dynamics, okay? But this illustration is quite helpful. You see that there's some time when you break down and your simulations start to become erratic. That's precisely the time when you fail to capture the norm of this state, because this representation involves these complex fields and actually is inherently non-Hermitian, and you have to average over a large number of these fields in order to get true unitary evolution. And what you can see is if you just take that noisy data and divide by the norm, you get much better agreement, apart from at this place where the norm is going close to 0, so you get a spike, okay? And this is just showing some extension of this work where we tried to actually combine this technique with matrix product states, where you could save the intermediate state as a matrix product state and then evolve that as a function of time, okay? So just to conclude, I think I'm nearly done. We've kind of managed to push this stochastic approach somewhat further than when I last talked about this. We can now start to look at Loschmidt amplitude in 2 and 3 dimensions. And there's quite a lot of directions for future research, including looking at quantum ground states through evolution in imaginary time. But the difficulty is to go to long enough imaginary times that you can do that. And also looking at other spin chains, higher spin. I mentioned this to some people over lunch a couple of days ago. I mean, it'd be interesting to look at this, for example, for the spin 1 chain. That's something we're currently looking at. That problem is not an integrable model, but this approach will not care. Okay, so you've got the ability to solve non-integrable problems, at least numerically, and write down explicit evolution equations. Okay, so it's not beyond the realms of possibility that if this approach is applied to some integrable problems, there might be some integrable structure of these stochastic differential equations. So I think I'm done with 1 minute to spare. Thank you.
Thanks, Joe. Questions?
So yeah, I just had, if you want to study transport in, like say spin chain, say say Heisenberg spin chain, say coupled to reservoirs and some non-equilibrium transport. Is there any hope to adapt this kind of techniques?
In principle, yes. So actually, one of the things I asked my students now to look at a long time ago, actually, was to try and extend this to open systems. Okay. And what he did is he managed to make a link that it was formally equivalent to an unraveling of the Lindblad equation. However, I think it's possible to go beyond that. Okay, so the logic was, I mean, you know, very often if you have some spin chain, you kind of inject something here, take something out there. My intuition is that there's nothing a priori in the formalism that needs the coupling to the bath to be weak. Okay, could be wrong about that, but I don't think so. So what I was hoping, and I think it's still out there, is that you should be able to go beyond the approximations involved in the derivation of the Lindblad equation, but in the appropriate weak coupling limit, make contact with that. Okay. The difficulty then is also the second thing, that if you want to look at transport, say, and look at a current operator, you've got to then say, can I actually disentangle that appropriately? Is it an observable that I can look at? Okay. But it could be that, you know, you could even look at, for example, the Loschmidt, the return probability in a different phase and see whether it has different signatures. So we have some initial work on generalizing it to open systems, but it's not been published. And I think the main thing that I wanted to chase has not been fully addressed.
The first one is regarding the error estimate. So nowhere on your curves I saw, like, you know, error bars and stuff like that. So how does the error scale, A, with the system size, and B, as you go longer in time?
Very, very good. So let me just show you one, and that's just a good job of putting it. This is unpublished. These are like estimate. Oops, sorry. These little light things are like estimates of the error, because they're telling you the variance in that quantity as a result of your stochastic averaging. Okay.
But is this just 1 over square root of, you know, number of samples, or
it's more let me show you. I've got a plot actually showing the killer. So it's actually a good question actually. So this is okay. This is showing you how the breakdown time depends on the number of samples that you need. And you see that beyond the breakdown time, you start to need an exponential number of samples. If I take the exponential, this number of samples needed grows exponentially with the breakdown time. So again, it's the no free lunch theorem. You get to this certain time scale, and actually you start to need to do enhanced sampling. Okay. One thing I've not been able to pin down, I know both Sam and Andrew Green think this is associated with entanglement growth, and certainly in a quantum spin system, you would expect entanglement to grow, and there's no question about that. Okay. The only thing I would say is it's not a hard and fast link in my mind between this breakdown of your inability to sample the SDEs and precisely how it relates to entanglement. Okay. But it's an interesting question, okay? And actually, this is the kind of killer, right? Because you say, well, I want to push this even further. So the difficulty is, can you break this exponential wall, okay? Now, what we've shown, if you go back to the use of these Weiss fields, okay, it's not that we've broken this exponential wall, okay? But what we have been able to do is push the simulation times much further than you might have expected without using these other tricks, okay? So it says there are things you can do to these SDEs that enable you to get to longer times. And then the question is that exponential growth as we've derived it? You see, bear in mind, all we're doing is brute force sampling of the SDEs, okay? So there's nothing sophisticated about that. And actually, if you're doing Monte Carlo sampling, very often you would have much more sophisticated ways of sampling your configuration space. This is just brute force unbiased sampling, okay? And actually, this trajectory average you can think of as a way to reweight the trajectories, okay? So it's like a way to kind of sample your phase space to get better results, okay? So that's how it kind of creeps in. So yeah, thanks for that. Yeah.
Growth of entanglement that you get. So can you do dynamics of systems where entanglement growth prevents you from using matrix product state methods. I mean, you show the comparison with I-tensor, right? Like you also show the 2D system, right? But I'm just asking about just the 1D system where entanglement would grow and then MPS would fail.
So what I would say is for 1D systems, do DMRG.
Okay.
2D systems, probably also the same actually with tensor networks.
Okay.
3D is starting to be a little bit different, okay? So what I would say is that it's not, at least at the moment, that we're outperforming any other method on the market. But on the other hand, it is a set of evolution equations that you can write down, okay? So you see, if you do some kind of path integral sampling or some DMRG, I don't know of any instances where you have a set of evolution equations that are formally governing your dynamics. And so if you're clever, maybe there are ways to analyze these STEs in ways we haven't done. What we have done is brute force sampling and show it works. And then, you know, the question is, can it be made more efficient?
Yeah. Okay, thanks.
Yeah, so I think we are slightly out of time, so maybe the other questions can be taken over lunch. So let's thank Joe one more time, and we move on to the next talk.